Our next speaker is Miguel Villoslada, who has used the computational capabilities of ESTHub, but used these for investigations of land processes, because as we have seen earlier today, lot of computations at ESTHub are done for benefits of mostly water related demands. But now the floor is yours, Miguel.
Yes, well, thank you very much, Martin, for inviting me today, and I'll just go ahead and share the screen. I hope you can see the slides, yes?
Yes, they are visible.
Good. Yeah, so what I want to present you today is how we have used ESTHub capabilities during the last, I think, couple of years to monitor above ground biomass in semi-natural grasslands in Estonia. And well, a little bit of context on this work. So this all happened in the frame of ELME project, which was actually, if I'm not mistaken, it was already presented last year. And it was coordinated, or it is still coordinated by Environmental Agency of Estonia. So the idea of ELME project was to implement basically the MAES process of the biodiversity strategy to 2020. So that mandate from the European Commission that every country should map and assess ecosystem services. So the idea behind the ELME project was to provide estimates on ecosystem condition and ecosystem services supply, and then integrate all these assessment into ongoing processes, so mostly environmental impact assessment and green network planning, nature conservation, environmental accounting, and so on and so forth. Specifically, in the case of semi-natural grasslands, we were very interested in producing national scale maps of above ground biomass, because this is strongly connected to habitat quality and fodder and grazing potential, carbon sequestration, even bioenergy potential. So in these semi-natural grasslands, we see that biomass is basically behind a lot of those services. So our requirements were that we want to have spatially explicit and nationwide assessment, and fine to medium resolution, so to actually be able to capture those relevant ecosystem dynamics. And most importantly, because we wanted to go in the line of the biodiversity strategy, we wanted to be able to account for ecosystem structures, functions, and services. So if you are familiar with the ecosystem services cascade model, so exactly what you see in the picture right there. Another reason why we wanted to target above ground biomass in semi-natural grasslands was to test this increasingly popular idea of wall-to-wall spatial data versus plot-based biodiversity monitoring. So plot-based biodiversity monitoring is basically what has been done in the European Union up to now, up to date. So it's basically based on local scale proxies and does not really account for multiple spatial scales characterizing ecosystems, and does not really yield accurate representations of, in the case of grasslands, of grassland status at regional and national level. And of course, very spatially constrained to the monitoring plots. On the other hand, if we would go to wall, this sort of raster-based biodiversity monitoring, then ideally we would end up with local, regional, or national estimates of biodiversity stock and change. We could account for multiple spatial scales, and in the case of grasslands, then account for grassland status and functions at different levels. And of course, this would be spatially unconstrained. So these were the motivations behind the work we did. And the aims very clearly being to map the above ground biomass over semi-natural grasslands in Estonia, all over Estonia. And the tricky part in here is that we wanted to account for various semi-natural grassland habitats according to Annex 1. So we were especially targeting alluvial meadows, coastal meadows, albars, and mesic meadows. Another interesting approach or view which we wanted to have is that we wanted to produce a multi-temporal assessment. So to be able to track the evolution of grassland biomass through time, but also to provide estimates of average grassland productivity. So, with these aims and these constraints, we realized that, Sentinel data, Sentinel-2 satisfied most of the requirements in terms of wall-to-wall data, nationwide estimations, and sufficient ground sampling distance, so this 10 to 20 meters per pixel. And ESTHub provided a extremely easy interface to do this basic processing, which was mosaicing, filtering clouds, and aggregating satellite data into medians or average, and etc. So what you see in the diagram down there, this was our basic workflow, starting from the ESTHub platform, basically getting average radiance values for June and July 2019. So June and July, we are targeting the peak vegetation period in grasslands. And then we also within ESTHub, actually, we calculated those 6 vegetation indexes that you see there. So EVI, GRDI, and the lot. We also included, by the way, soil organic carbon from the soil map of 2019. So all that information that came straight from ESTHub was fed into a random forest algorithm, and then we use a rather large training data set of more or less 500 samples across 4 grassland habitats, a little bit more on that later. And, basic machine learning process of training and validation. And we got the above ground biomass maps for 2019. But also we implemented a backwards training approach, which allowed us to create above ground biomass maps for 2016, 17, and 18. So having those 4 years of biomass, then we were able to average all that into what would be average semi-natural grassland productivity. About the training data set, this is one absolutely crucial step anytime that we're dealing with supervised machine learning. So again, there were a number of demands which we wanted from the training data set. So it should, of course, account for the functional variability, which translates into spectral variability of the semi-natural grasslands targeted. Remember that we are looking here at albars, alluvial meadows, coastal meadows, and mesic meadows as well. So different in many ways, different in species composition, different in sward structure, and different in their spectral variability. The training data set should also be as spatially dispersed as possible to avoid local bias and be able to capture environmental variability. And of course, the samples should be collected in the same year. So 2019 was our reference year for ENME project. So the samples, the training samples should have been collected in 2019 and roughly in the same month, June, July, which we were targeting with the ESTHub products. And the whole training data set should be large enough. So we were lucky enough to come across different research teams from Tartu Ülikool and the Estonian University of Life Sciences who had been doing fieldwork campaigns in that year in 2019. So we have, for example, Indrek Meltz, who had been surveying alluvial meadows, and Avelina Helm, who had been working quite a lot in Alvars, and then my team was working on coastal meadows at that time. So we managed to put together initially 700 biomass samples, which were then reduced to about 500. Like I have said already, across these 4 habitats: alluvial, alvar, coastal meadows, and mesic meadows. And the main issue we found with the training data set, and this is of course normal if you haven't planned for such a large campaign, is that we ended up with a very imbalanced sample set. So the most of the samples came actually from coastal meadows, and for instance, very little from floodplains. Another important issue is that when dealing with such small training samples at the plot scale, so let's say 1 by 1 meters or even 50 by 50 centimeters, and then you have data coming from Sentinel-2. So there are issues related to spectral mixing, especially in certain types of grasslands where we have trees and shrubs scattered. So we had to do quite a lot of filtering of the training data set. So plots measured in grasslands with over 30% of woody canopy, those were immediately discarded. That would be the case on the image below. And then also plots that contained a tree or a shrub in a 20-meter radius were discarded. So that's the situation in the image above. So that's how we went from around 700 samples to around 500 to ensure that we had more or less, or that we were avoiding spectral mixing in the training dataset. And that's how the training dataset would look. So of course, most of the samples come from West Estonia, and again, so we had to deal with this class imbalance issue, and there are several issues, several ways to approach this class imbalance. So you could have weighted random forest, or equal sample, or downsample random forest, or maybe a bit more modern approach would be extreme gradient boosting. What we used was equal sample random forest. So we ran, if I'm correct, we ran around 25 random forest algorithms in parallel with equal sample sizes, and then averaged. The input data, in this case, it was, like I said before, 6 vegetation indices calculated all over Estonia. So with the help of the ESTHub platform. The idea to use a wider range of vegetation indices is to avoid the shortcomings of individual indices, especially NDVI, which may show some weaknesses in the case of meadows that have a significant amount of moisture saturation in the soil, for example. And the more indices that we incorporate in the algorithm, the more information we are conveying about the grasslands. So anything related to vegetation status and vigor, pigment content, and etc. So what you see there in the image is 2 different indices, so NDVI red edge and the usual NDVI. Like I said before, calculated over the mean reflectance values between June and July 2019. So I have to say, pretty clean and good-looking mosaics all over the country extent. And these would be the results of our equal sampled random forest. Of course, if you look at it at the scale of the whole of Estonia, then it's hard to appreciate the detail, because this is just those tiny bits of semi-natural grasslands. But what you have on the right is a zoom into Matsalu and in Silma protected area in the north. And you can very well see already the patterns of grassland productivity, the differences between flooded meadows, much more productive, and then basically all along the coast, that fringe of coastal meadows with lower productivity, and also because they are being constantly grazed. And then scattered here and there, I think you would have some of those alvar meadows as well. The validation results actually were better than expected. So, and if compared to the scientific literature on the issue, quite good. So we had an overall R-squared of 0.7, and then the root mean squared error range between 70 and 200 grams per square meter. That depends on the grassland type. Regarding validation, we think it's very important to address uncertainty. So, starting from the idea that any map is an oversimplification of reality and any model is necessarily an oversimplification of ecosystem functions. So we need to somehow address this uncertainty. And the idea here is that beyond overall accuracies of models, we need to report some sort of disaggregated values by biomes, by ecosystem type, habitat, depends on the scale of your study. So, and of course, reporting validation and uncertainty forces us to be, very open about our processes and our data, and leads to reproducibility. So we had this overall R-squared value of 0.7, but we were wondering, what happens if we break this validation into grassland types? What will we see? And what happens is that, for instance, flooded or biomass in flooded meadows was very well modeled with a 0.8 R-squared, whereas in alvars, the value dropped to 0.45. And this is expected because of all the spectral mixing that goes along in alvar meadows if you compare to the very homogeneous sward structure of a flooded meadow. And then coastal meadows were more or less in between. So that was for 2019. But like I said before, we wanted to sort of have this or address these temporal scales as well, and be able to see shifts in grassland productivity through the years. So what we did is this backwards training approach, where we used this training data set of 500 samples coupled with the spectral values of the various vegetation indexes for 2019, and then applied this back in time for spectral values or for vegetation indexes in 2016, 17, and 18. So, and the idea was the same, average values between June and July, so peak vegetation time. And what we get is these sort of maps where we can see biomass change at the landscape level. So you can see the evolution or the shifts in productivity from 2016 to 2019. This is a zoom into Silma, Loguskaitsela, and patterns in this area are rather stable because these are anyways coastal meadows that are mostly managed in exactly the same way every year. So we expect the same grazing density or grazing pressure. So we wouldn't expect huge changes in productivity. Then we have here a zoom into basically Emajogi alluvial meadows between Burtsjärv and Kärevere, and same thing between 2016 and 2019. Actually, most of these meadows are not managed in any ways, so we expect a little bit more of to see a little bit more of that biomass variability. And what sort of things we can do with these maps at the landscape scale is to detect hotspots of productivity change. But it's very important to keep in mind that when we are looking at this sort of change, we need to be able also to address, to allocate change, to make sure that we know the reason behind that change. For example, in coastal meadows, if we see in some cases a drastic decrease in productivity, we could expect that there has been a reed cut. We can approach the same issue, but at the plot level. So we have here two contrasting situations. The first image is Kemu Peninsula in Matsalu, so coastal meadow, and then below we have alluvial meadow in Kärevere. So Kemu, it's been constantly grazed and managed, and you see that the trend shows actually a small decrease in 2018 and 2019. But for the same years, the trend is different in this alluvial meadow, which shows a very smooth increase in productivity. So with these plot level assessments, if we disaggregate these assessments by grassland type, then we can see local trends, we can see the effects of management, we could see the effect of local weather conditions within the same year. And so back to the ELME project, which was the originator of all this work. Remember that what we were actually looking at was ecosystem services, but so far we have just talked about grass biomass, which is rather primary productivity, maybe an ecosystem function. So how does this above ground biomass translates into ecosystem services? We need to use further indicators. So one of the services we addressed was the potential use of semi-natural grasslands for bioenergy production, very much inspired by the Lihula municipality boiler house. So what we did is simply we took the basis of our average biomass values in grasslands, and then we plugged in a set of conversion values or indicators that Indrek Meltz had developed in his earlier works. And this way we moved from this ecosystem function, this biomass yield, to an actual ecosystem service, which was the potential energy yield in terms of calorific energy, which is actually classified as an ecosystem service. And just to finalize how I see the way forward, I mean, the experience with the ESTHub platform has been extremely good. And I see so much potential that perhaps is being slightly unused. So I think that ESTHub presents a great opportunity for multi-scale biodiversity monitoring, especially now when it seems that countries are moving towards this more remote sensing based monitoring of biodiversity stock and change. So using these sort of approaches, we could tackle some of those well-known shortcomings in biodiversity monitoring, which is mainly lack of data at multiple spatial scales and lack of spatially and temporally explicit data on change. One thing that, and I think Leah has mentioned this before, and I think this is very important, is the use of UAVs. We have at this point in time advanced quite a lot in terms of UAV remote sensing and algorithm development. And I think UAVs combined with satellite data would be extremely useful to disentangle this sub-pixel spectral mixing associated to trees and shrubs and etc. But most importantly, we could improve the training of machine learning algorithms. So, you know, what I have explained so far is the use of biomass plots, which are at best 1 meter in size. And this is used to train 20 meters per pixel resolution of Sentinel. If we are able to have the UAVs in between as a segue for training, I'm pretty sure that we would get much better estimations. And what you see there in those two images is the same area in a coastal meadow in Silma, in Kudami, more specifically. So on the left, UAV-based biomass estimation at 10 centimeters per pixel, and on the right, the same year, same moment in time, Sentinel-2 biomass estimation at 20 meters per pixel. So I think the way forward is the fusion of these two elements. And that was my last slide. So I'd be happy to answer questions if there are any.
Thank you, Miguel, for very interesting and thorough presentation, and also about these future ideas. I think already we have started with joining the datasets of European space agencies, and the land boards own currently one plane. So one step is already done, but okay, thank you once again.